Great. So we got to this point where the extremal f satisfies this relation here. The right relation and so on. So there are two comments. Well, the first comment is really that this says that we can think of f as of a measure on the boundary. Why? Well, because okay. And here is my alpha plus minus, and consider here we are at the boundary level, and let me call this set here S of alpha, or maybe I should write a boundary of S of alpha plus a boundary of S of alpha minus, where the definition is this: the boundary of S is like success, so to say, of alpha is by definition the set of all points in the boundary. That's why I put this partial here, so that alpha belongs to the vector set. Because if I pick a point here, when I go to the pre-root, I have to pass through. When going from the pre-root to x, I have to pass through alpha. Now, if I let the measure of S of this thing and alpha defines the measure. Defines the measure. Because of that, because the measure of a set is the sum of the measure of the two parts which actually the set. Okay. So here we are in a finite, analysis, so there is no problem of measurability and this kind of things. So once I do this, defines the measure. In fact, this this is the equilibrium rate. It will be, how to say, an object we're interested. Okay. And now, so since this is a measure, so f of the edge, f computed at the edge alpha is additive in this sense. Then it defines a measure on the boundary of the tree. Okay. And now we have timings, because now we have timings Okay, this can be interpreted in terms of patterns. Because let me consider, okay, one could write this formal, but let me consider that this is not the hour to do that, and it's not even useful. Let's consider this tree with that boundary. And then, okay, so these are x, y, z. And let's call these alpha x, alpha y, and alpha z. Well, so we have that the measure mu, defined like that, of x is simply f of x, the measure mu of y is f of alpha y, and the measure mu of z, f of alpha z. Now, but since we have the additivity, okay, if this is mu of alpha z, if this is mu of z, this is mu of z again. I mean, this is f. This is we said it's mu of y. Additivity. This is mu of z plus mu of y. This is mu of x, and this is the sum of these guys. Mu of x plus mu of y plus mu of z. So this is the picture. And the sum of these guys has to be 1, which means the sum of this and this is 1, the sum of this is 1, this is 1. So in a picture, that becomes that we have okay, so this is this alpha, or sorry, I don't call it anyway. So I start, let me do the timing maybe instead of okay. So maybe I want to make it a bit bigger. But then there is this guy here, but this guy splits into 2 parts. One which goes maybe to be, which goes down to the boundary, and the other takes a while to go. The tiling, the corresponding tiling is something like this. Because the corresponding tiling has size mu x, mu y, and mu z, which are precisely satisfying this thing above there. So this is mu z, this is again mu z, this is mu z, mu y plus mu z, and this is mu x plus mu y. So here, and the requirement it is that if I sum this and this, I get 1, exactly like that. If I sum this and this and this, I get 1, and this, and this, I get 1. So the solution to that problem is also the solution to this kind of thing. Okay. And this is for all trees, for all finite trees. Right. So I take this to be a proof of So we okay for the extremal picture. For the extremal picture, so maybe this is a point. I don't remember which point. Okay, this was point 6. You find it in the notes. Point 7. But are the solutions unique? Is the solution to this problem unique? Okay, because this solution, at some point we use Weierstrass here, which doesn't say anything about uniqueness. And in fact, it is unique. Right? Convexity. So the extremal F is unique. In fact, suppose you have 2. Suppose that F1 and F2 extremal, which means that I F1 is equal to 1 equal to I F2 boundary in particular, then if I take F1 plus F2 over 2, well, the sum of this thing is 1 boundary, and if I consider the 2 norm, this is strictly well, that's less or equal by Jensen's inequality or Cauchy-Schwarz or whatever you want. This one which is the minimum, the famous minimum. So it's better having equality here. Otherwise, we found a better one. But to have equality in Cauchy-Schwarz, you need to have equality in this inequality. You need this to be the same. Okay, proportional. But if they are proportional and you are requiring this, they have to be the same. Okay. So that implies that you have either strict inequality or F1. That's about uniqueness. What about the energy? What about the energy? Because we said that we are interested in energies and things like that. So remember that the energy of mu, where mu is a positive function of the boundary, that this was the integral, but in this case it's a sum of the p prime power, which in this case it's 2 power of k check mu. For alpha in the n, which is in this case what is k check? K check mu, I should have said it before. It is like the integral, but actually it's a sum for x in the boundary of the tree of mu of x times characteristic function of x of alpha belongs to x. But this is the same characteristic function of x belongs to the s of alpha, because that's we defined kind of so this really is the measure of the s of alpha. Oops. It is the measure of that. So the energy is sum over alpha, the offset of the measure of the s of alpha squared. For which, by the way, we have an official name, and the official name is I star, like a joint of I, mu of alpha squared. So what is the energy? Because we have timings. Because mu of S alpha, if you remember, okay, let's make this simpler timing like that. Okay, this is like mu x, this is mu I. Okay, mu of and I and f, the extremal f gives me the side of these squares. So this thing here is the area of the rectangle, because it is the sum of the areas of these squares. The area of the rectangle, which is 1 times some capacity. So we can catch this, that the energy is the capacity for the extremal mu. Something which we meet also in the general field. Well, okay, and then there are a couple of other things that at this point I so let me make a summary of what we have seen. If this is my definition of, by the way, let me make so this is another way this, which makes it easier somehow. Okay, consider it. Consider a tree which is fixed into n, let's say, a fixed dyadic tree, not subdyadic. This is a really dyadic tree. That's n. This means that I start from the voltage, and then I divide, and then I divide. How many times I want to divide? maybe n times. So I start at 0 and then 1, 2, blah, 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 until I divide n times. So boundary of this tree, let's call it T, the has 2 to the n points down here. And now, okay, so I make a picture like that. Now, pick a subset of vertices. So this is my tree, this one. Pick a subset of vertices. Possibly of a stopping type, so it means if I pick a point here, then I do not pick points below it. Maybe I pick this point here, and then I do not pick anything below, and maybe I pick these 2 points here. Okay. And let's say that this is my set E. And then I can find TE, okay, this is the root. TE is the tree it is the smallest subtree of the original one containing E and the root. So I want this to be there, I want this to be there. So essentially is like that. Like this. And essentially all of sublayer trees can be obtained this way. And then we define a capacity at this point. Okay, this is just I just want to see my tree as a subtree of something else. Actually, here it's not even needed to put that. Find it. I want to find it set like this. I will continue infinitely later. I just find it objects. Okay. At this point, the capacity of E is by definition the capacity of that thing. So you might complain now. I mean, there is a possible complaint because we have this function f. What if I put some weight here, or maybe what if I put some weight in some edges which are not involved here? Well, if I put some weight on edges which are not involved in this picture, I'm not changing IF at these points first, and I'm making worse the sum of the F squared. So for sure, when I look for extremers, the support has to be there in this tree. Okay. All right. By the way, and let me make a further observation, because those of you who have seen some variational arguments, either in analysis or in physics, and so on and so on, could recognize something classical, and in fact, that's true, which is that what we are saying here, but for the what we are saying here, but for this recursive formula, which is very special, recursive formulas, you don't have them in potential theory, except in this case. Well, you have a recursive. In this case, maybe you have P different than 2. Maybe you take infinite trees and you still have recursive formulas, but when you leave trees, you don't have any recursive formula of any kind. So things are, so you only have estimates. But okay, there was a feature maybe you have a problem, which is that this. When I say that, f of alpha is equal to f of alpha plus, f of alpha minus, and if I consider capital F of x as the sum as I f of x, which is the sum over here of f of alpha, f of beta. Okay, let's call this point x and say that this point is x plus, this point is x minus, and this point is x minus 1, like predecessor length. Somewhere here there is a pre-root. So capital F makes the sum of little f on the test up to here, or up to here, or up to here, or up to here. Now, when you consider f of x plus, plus f of x minus, here, here, and that, plus f of x minus 1, what you get is, well, f of x plus, it is like f of x plus little f here, f of x minus another f of x plus little f of little here, and f of x minus 1 is equal to f of x minus f of alpha, Well, you have 1, 2, 3, so that gives you 3 f of x plus this minus this, which is 0. So what you have for the extremal f, it is a mean value problem. Which is that f of x is equal to f over 3. So it's the capital F computed here is the arithmetic mean of capital F computed at these 3 points. Right. Some of you know that mean value properties arise when you have harmonic functions, and in fact the equation Laplacian of u is equal to 0 can be read as a mean value property at the infinitesimal level, in fact. So it means that these functions are harmonic in this sense. Well, not the function little f, but I of little f, which is the potential, right? I little f, which is say the potential. So the potential is harmonic in this sense, satisfies the mean value property. In fact, from the mean value property, like in you get the maximum principle. So this function mu satisfies a maximum principle. It cannot be maximum here because here it is the average of these guys. Right? Not everybody is better than average. That's basically the thing. And in fact, much of what I said can be done with the derivatives and the complications and so on in this more classical setting. Here, let's say that so if instead of the tree, I take the disk. So instead of the tree, I take the disk. Instead of the boundary of the tree, I consider the boundary disk. Well, maybe it's the disk with a because there is this other thing. Maybe it's the disk with a hole. Okay, instead of the boundary of the tree, I take the boundary of the unit disk here, and instead of minimizing this thing, what I want to minimize that. Where the function u plays the role of the function if here. And you have pretty much an exact correspondence. So if you want to externalize these, given certain boundary values, you get, if you want to minimize these, where u on the boundary of the disk, let's take the disk. The boundary of the disk is some function phi. You get a harmonic function. If you want to minimize these, given some restriction on that, you get a function which satisfies this mean value property here. Okay, so that's all for today. And right, next time I probably will go through step forward into axiomatics here. So my idea is to jump to do axiomatic theory, and then to consider examples of axiomatic theory, examples, and so on. And at some point, we have this. We should have to learn something. By the way, this kernel K we consider it is a kernel in which the space X and the space M are different. And the kernel is not symmetric at all. It's not symmetric at all. It's very asymmetric. So I mean, even if I wanted to identify alpha with a vertex like at the end of alpha, but anyhow, our kernel is much different. Essentially because it is the same difference that there is between this and this. Then this is some hyperbolic geometry here. Maybe we make it explicit somewhat. Okay, well, thanks for nice weekend. Yours.